Have you ever wondered where L2 loss function comes from? It is one of the most popular loss functions that is being used to train regression models that predict a real valued number. But how it is actually related to Gaussian distribution? Well, that's what we're going to find out in this video. Hi everyone, welcome to Deep Dive Bites, where the goal is to have quick visual deep dives into the topics from a wide range of computer science, including AI, image processing, and programming. So if that's your thing, hit the subscribe button, and without further ado, let's dive right into it. Let's assume that our dataset is given as x and y, which x represent our inputs that could be images, videos, or tabular data, and y represent the real value, the expected outputs from the model. For example, imagine that we are predicting the price of houses based on their square footage. So assuming that our dataset is given by these blue dots, the goal is to fit a curve into the data that represent the blue points as best as possible, such as this yellow curve. And to find the error of the model, we take each individual point and find its distance to the yellow curve, which is shown by the red dashed line for each individual point. Now, the outputs of the model can be written using this formula, which the first part, highlighted by the green rectangle, represents the dot product between the parameters of the model theta and the inputs x sub I. So assuming that our model has n parameters and our input x sub I has also n input features, we can represent both with column vectors, which are basically matrices with only one column. Note that by convention, all vectors in textbooks are represented in fact as column vectors by default. However, since these two column vectors cannot be dot products since the shape doesn't match, we take the transpose of the parameters theta to make the dot product happen and to get the final model output. The second part represents the errors that we have in our outputs. For example, in the case of predicting the price of houses, it could be features that are actually pertinent to predicting the house prices, but we did not utilize it, or it could be a random error. So the big assumption that we make here is that this error, epsilon sub I, is a Gaussian random variable with mean of 0 and variance of sigma squared, which is technically called a normal random variable. So summing things up, we have the first part, which is a fixed constant when the parameters theta are found, and we have the error of the model being represented by epsilon sub I, which is modeled by the Gaussian random variable. Hence, y sub I is also a Gaussian random variable, which is shifted by a constant. As a reminder, assuming that we have a Gaussian random variable z with mean mu and variance sigma squared, then if we add a constant to it, it will be added directly to its mean value, resulting in its new form. Now, replacing our epsilon and our constant here into these equations, we can see that we have Gaussian random variables with mean theta transpose dot x sub I and with variance sigma squared. Hence, we reach the big conclusion that our output, y sub I, is also a Gaussian random variable with those mentioned mean and variance parameters. So we know from our previous video, which the link is in the description below, that the output of the model is written with a conditional probability. And we know that we want to maximize the log likelihood function, which sums up all those conditional probabilities. Assuming that Gaussian random variable z has a mean of mu and variance of sigma squared, the Gaussian distribution formula can be written as this. We also know that y sub I is also a Gaussian random variable. Hence, replacing its mean and variance into the formula, we can get the Gaussian distribution for y sub I. Now, replacing the distribution formula into the log likelihood function, we know that the logarithm turns multiplication into summation. Then, separating these equations from each other and focusing on the first part, we observe that none of its variables depend on the summation index I. Therefore, the summation simply contributes a factor of n, yielding n times the expression inside the summation. Moving on to the second part, the first thing that happens is that the natural logarithm cancels out the exponential here. Then, taking out the variables that are not dependent on summation index, we reach a new form that we replace inside our log likelihood formula. Now, if we look closely at the first part highlighted by the red rectangle, we can see that the parameters of the model theta are not presented here, meaning that this part does not have impact on the likelihood maximization, can be regarded as a constant, hence omitted. As for the remaining part, similarly, those parts that are constant can be omitted to further simplify the equation. Finally, since we have a negative sign, we can remove it and turn our maximization of log likelihood into a minimization. And there we have it. We have the famous mean squared error loss function, which is being used to train many regression models, and to find the best set of parameters, we will minimize it. And with that said, we have reached the end of this video. Thank you all so much for watching. If you found value in this video, please consider liking and subscribing to support the channel. And if you have any questions on your mind or any topics that you'd like me to cover, please feel free to share them down below in the comments section, and hope to see you all in the next video.